don't have to really go through them. I'll just touch the highlights because these slides are already posted on the IOTA JHU website. In the message I sent out a day or two ago, you can see the link to them. This particular presentation was one that I made to set up a poster presentation that was given at the Asteroid Science in the Age of Hayabusa 2 and OSIRIS-REx in Tucson last November. So you can see all the people that were involved in the occultation campaigns for Phaethon. All the people who especially contributed professionally or organizing the amateurs couldn't list all the observers that we had here, but we thank everyone who participated in that great campaign. But I've updated this to just made a few additions, removed a few slides, and have one new slide. Just go through an introduction about Phaethon, and then about the July 29th occultation. It's already been mentioned, of a 7th magnitude star. And then 2 months later, there was another faint occultation in California, about 12.5 magnitude star. So although it was faint, it was important to predict the future occultations in October, which was successful. Since I had to give some background about portable remote stations, I have a couple of slides on that just so you can see that, but I've talked about that at previous meetings more extensively. And then some conclusions, future work, and resources. Anyway, this just goes through about Phaethon. It's already been mentioned. It was the first asteroid to be discovered by a satellite, the IRIS satellite. It's the parent body of the Geminids meteor stream. It puts on I think the second largest annual meteor shower after the Perseids in August. This mysterious object may be a nearly dead comet nucleus, or probably more likely it's a very active asteroid throwing off boulders, like has been seen, observed on Bennu by the OSIRIS-REx mission. Phaethon is an Apollo asteroid with perihelion of only about half of Mercury's, but it has an aphelion way out in the main belt. So there's huge thermal shocks every perihelion as this object comes close to the sun. Fairly significant non-gravitational forces have been detected in the past. Anyway, Phaethon is an Apollo asteroid. I already just mentioned that. Also, as mentioned, the Japanese Destiny Plus spacecraft plans to fly by Phaethon in 2025. And of course, radar observations show Phaethon to be nearly spherical with a diameter of roughly 6 kilometers. But the Destiny Plus team was quite concerned because thermal IR data give a diameter of only about 4 kilometers. So they wanted to know, for their imaging and everything, because it's going to be a fast flyby, of the best way to image that. They want to know the size and the albedo and everything they can about the asteroid. On that basis, this event was first identified by Isao Sato in Japan in January 2019. He alerted us to this event, and Steve Preston put it on his webpage. To obtain an accurate astrometric point for orbit improvement to resolve the diameter discrepancy, Tomoko requested that NASA try to get and IOTA try to observe this rare event. But this was by far the smallest object that IOTA has tried to predict and observe, and we needed help. So we had a collaboration with Swiri and Mark Bowie and others to do the best we could with that event. And as Dave Harold pointed out, we had to, this really shook up the software, and all the little details that we could ignore in the past came out glaring. And anyway, to start the effort, George Giorgini with the JPL Horizons team computed solution 684 after including radar measurements that were made in 2017. Then David, let's see, the 684, you can see this error bar here, error ellipse, but then David of Fornotia computed JPL 685, which is, this shows the error ellipse in the sky plane for the July 29th event, considerably shrinking the error ellipse by manually including Gaia astrometry. And that was the key to getting this prediction. But we really were uncertain how good the prediction really was. It looked great on paper, having only, you know, these are 3 sigma error ellipse, and it's only 10, 15 kilometers across. So we could really, this asteroid, because of the non-gravitational terms, it wasn't really certain how much of an effect that would have on the actual orbit. You know, there were other people who predicted it having quite different paths, but you know, this looked really good. But we just decided to throw out a bigger net to cover, you know, about 30 kilometers north and south of the path to really be sure. We're not quite that big. It was, you know, about 20 kilometers or so. We, the next slide shows the lines that were set up in an interactive map that Swiri sets up like they use for the MU-69 campaigns, but in this case, the spacing was only about 680 meters between the lines. And so we had 70 lines that we wanted to try to record. This is the 3 sigma zone is shown between the green line, well, between these 2 white lines here. The green lines are the ones that Swiri said, okay, we'll set up our sky watchers, which sort of a huge hammer to hit such a bright star, which could easily be recorded with mighty minis. Anyway, so we put out a call to observers to try to cover this pattern, actually of 66 lines here. And all 66 lines were assigned to the many mobile observers who volunteered, including several who planned multiple station deployments. But in the end, 9 lines couldn't be actually filled for various reasons, and another 10 failed to get data for different reasons. You know, we ran 11 stations in the oil fields south of Bakersfield, 7 of which recorded the star with no occultation. This just shows the occult watcher plan for the observers in Las Vegas area. This shows the sky plane plot. You saw the intent to get everyone lined up on those nice even lines, but the one thing Mark Bowie's map did not take into account was the height of elevation above sea level. And some of these stations were over a mile high elevation, the ones in Colorado, and whereas we were near sea level in the San Joaquin Valley near Bakersfield. But anyway, this shows, this was Dave Harold had shown something like this. The Horizon's prediction actually was accurate to less than the radius of Phaethon, and actually was under about 1.5 kilometer accuracy, thanks to those Gaia and radar observations. So we shouldn't have been concerned. We should have believed that 3 sigma. I talked about the elevation correction here, which we always apply for lunar grazing occultations, because some of the elevation shifts were more than the 68 meter separation between them. So that's why this happens. And John Moore, of course, produced this plot. This shows a zoom in of the shape model fit that Dave Harold did. It did provide accurate information confirming that confirm the radar value for the size of the asteroid. And of course, the shape is quite well known from the radar observations too. But the important thing is this gave us an extremely accurate astrometric position, which they also desperately wanted, that would help predict future occultations. And the next future occultation, there was one on August 21st in Japan, which there were these 3 events that were all clouded out. Masao Sato predicted the ones in September, and also one in October 16th in Japan that was also clouded out. So he had some bad luck with those other events. But then I predicted some events, including the September 29th star. It was 12.0 magnitude, but the actual V magnitude was below 12.5 from the AAVSOA pass. So it was a really faint target. So we used our own interactive Google map by Derek Bright, and used a spreadsheet which took into account the height above sea level correction, so we could create lines across this at 1 kilometer intervals. So anyway, this shows the pre-occultation solution. On the September 29th sky plane, the dotted line is the motion, but then lines 705 and 707 were the air ellipses that were computed by the Horizons team based upon the astrometric point for July 29th provided by Dave Harold, and another similar calculation by John Irwin. So we wanted to cover, the 2 sigma limits encompassing both these 2 predictions. Plus the radius of the asteroid. So we set up 17 bands, 635 meters across. We couldn't cover anywhere near those, but if we could cover every other one, we would have about 1.2 kilometers. We'd get the good astrometric point that we wanted. There was this 20 mule team parkway that we were able to set up our multiple stations on, and Bob Jones took one of the lines with his 20 centimeter telescope, and so we had these lines A01 to A09, which we occupied each of them, and Greg Lazenga set up about 80 kilometers to the south of us near Lancaster, California. He was planning to observe in the LA basin, but rain clouds came in, so he went out into the desert, but he didn't get far enough. The clouds actually affected him there. So we're not sure if he got an occultation. But we had 2 10-inch suitcase telescopes, which we placed near the center. They're near the south limit. This is shifted. This limit is for the non-elevation corrected, but if you take count the elevation correction, these were near the predicted center. The problem is the other 2 stations used only the 120 millimeter maxi telescopes, which were really not suitable for this star. They did show it with the run cams. We were using run cams for all of these, and we used the maximum integration with them, but they just barely detected it. We think we got a detection in the AO3 one. It's AO5 and AO6 are clear. We had strong wind shake. There's windy and no protection to there, but fortunately for the crucial 10-inch scopes, the wind died down, so there wasn't any wind shake during the occultation for around 20-second period or so, surrounding it 10 seconds or so. But the target was faint enough that there were troubles with the analysis for these events, and that would be the subject of another talk, which I can't go into here. and the actual observations. We had to do this quickly because the October events were coming up. We had to get this data to JPL so that they could update the orbit and nail the predictions for the 4 occultations in October. So they issued solution 711, issued on October 8th, using the astrometric points from both the July 29th, July and September occultations. It proved to be so accurate that no other updates were needed. And successfully predicted all 4 of the other occultations that were each observed from 2 or 3 stations. I learned later that the JPL Horizons team was pleased that the solution allowed a determination of Phaethon's non-gravitational parameter to a 9 sigma accuracy, while before the July occultation it was known to only 2 sigma. So this was a remarkable achievement of the effort. And I talk about the different events. The July 12th event, 2 mobile stations from the University of Virginia got that near Richmond. I was considering going out there, but the weather forecasts were uncertain 2 days before to justify a plane trip. And so I decided to cancel. I knew that there would probably be some clear sky somewhere in Virginia, but wasn't sure where. I guess I should have jumped and done that. We were living in Arizona at the time. If we had been in Greenbelt, of course, we would, like we are now, would have been duck soup. But it was a brighter star that wouldn't have had the issues of the one that we did in September 29th. And then October 15th, 10 stations were deployed in Japan across the path. They used QHY, or they used different cameras with 20 centimeter SCTs, but it was mostly cloudy, and only 1 station really got a good detection, and they claimed a possible central flash, but considering the noise, I'm sure pretty sure that wasn't the case. We didn't see anything like that in July with a much brighter star. But this just shows the possible chords from the Japanese analysis. Then, so there were 2 events on October 15th, and the second one was in Europe. And curiously, Paulo Tanga, who's on the Gaia team, he led a team, including other co-authors from the Observatoire du 14 to a site 700 meters from the predicted central line using a portable 1-meter telescope and a QHY camera. And they ran it at 120 frames per second. They had some drop frames, but none during the event, which preliminary analysis showed they had a 0.22 second occultation. But this is a remarkable telescope, but of course takes some effort to transport and assemble. There were 2 other observations of this occultation, but they weren't really coordinating like we were or anything. Well, they all just went towards the center line. On the 25th, there was another occultation that was observed from Italy by 2 observers using the CCD drift scan technique. But interestingly, both the October 15th and the October 25th occultation paths crossed Algeria, and I can't pronounce his name, ISATA, used a portable 20 centimeter SCT with an IOTA VTI video equipment to successfully observe both of these occultations. So he's the only person who has actually observed 2 Phaethon occultations, only 10 days apart. So anyway, after Phaethon in December, the Phaethon dust trail was actually imaged by NASA's Parker Solar Probe. See the line here. This just gives the information about it. Anyway, after that, I gave just a rundown about using, running portable remote stations. Too many, and as pointed out, too many asteroid occultations are observed from only 1 station. it's much better. Information can be obtained if the event can be recorded from 2 or more stations. We describe here how that can be done, and I don't really have time to go into that now. You just point a non-tracking simple telescope on a rugged mount to the altitude and azimuth of the target star. We'll have and keep it fixed at that location using the 3-point line of declination, which I showed in the previous talk. Let's just go on to the next slide. This just shows one of our examples of a portable station that we ran for an event that's described in JOA issue 2019, number 1. In that case, it was on a paver mount, and we talk about how the available dark time, but if you can use these paver mounts, allow you to set it up on a paver stone that you can leave in the behind a tree or in the desert or wherever, and then just gently return the telescope to it so you can pre-point it the night before. So that gives you a lot more time and you can run more stations. But anyway, this shows the 10-inch suitcase telescope then that can record the fainter occultations down to the 13th magnitude stars. And this is John Broughton's. He has a great presentation in the TTSO website. You can go to it and see his presentation there about specialized telescopes for occultation observing. It's only 30 pounds and collapses to fill about 60% of a standard airline suitcase. Anyway, talk about future things, and we plan to publish a paper about this with Mark Bowie at some point when we get a chance. I've already gone through the major parts, and I made a plea, for the asteroids science conference. And I sort of made a plea at the end. We would like to collaborate with college or university astronomy departments to develop ideas and recruit students to help with multiple station deployments for asteroid occultations. Improved versions of our equipment could be used for some TNO events. Most of us doing this work in IOTA are elderly, and we'd like to pass on our work to future generations to get more young people, and going through colleges and universities is the way to do that. Of course, astronomy clubs as well, I think to actually reach the younger people, there are actually more of them are students. If they have to do a homework or have to do an assignment, I think Alex Knox is a good example, great example of a young person who's made great contributions. Anyway, this presentation is available there, and I'm going to finish this presentation, and so we're only less than 10, well, let's see, not, okay, yeah, about, I made up a little bit of time, but I think I'll go on to the last presentation, which